Good afternoon, class. We are looking at pre-calculus practice test number 2, module 2, that covers chapters 3 and 4. Here's chapter 4, exponential and logarithmic functions. Here's the first part. Again, reminding you of the pledge when we take the exam. We are going to assume we are taking it on campus and we are taking the exam by ourselves, following the rules. All right, find the formula for an exponential function that passes through these 2 points, 0, 2000, 2, 20, and f of x has the general formula a b to the power of x. So basically, you want to find a and b to do, so we have 2 pairs, we plug in and we solve the system in essence. So if you plug in 0 and 2000, you get a b to the power of 0 equals 2000. And if you plug in 220, you get ab squared equals 20. So b to the power of 0 is 1. That makes a 2000. Which makes the function f of x equals 2000 times b to the power of x. Now, f of 2 is ab squared is equal to 20. So we are going to put 2 in here, and we know the answer is 20. So 2000 b squared is 20. Let's divide both sides by 2000. We get 1 over 100. Let's take a root. B becomes plus minus square root of 1 over 100, which is plus minus 1 over 10. And we can't have a negative as the base. F of x is 2000 times 1 over 10 to the power of x, because for the exponential functions, the restriction is that the base must be positive and it can't be 1. Let's move on. Liz deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it is compounded monthly? So first, what are those? A is P times 1 plus R over N to the power of NT. This is the compound interest formula. Remember, I equals PRT is the basic simple interest. This is the compound interest. So the amount of principal, $10,250. Rate is 4% or 0.04. T is 10 years. Now monthly. N is the number of compounding that takes place per year. Annually, N becomes 1. Monthly, N becomes 12. So that's the general formula we're going to use. And for this case, we use N equals 12. So all you have to do, replace the N with 12, use a calculator, come up with the answer. So $10,250 times 1 plus 0.04 over N, which is 12, 12 times 10, which is 120. So add these two numbers, raise it to the power of 120, multiplied by 10,250, and you get $15,281.03. By the way, when it comes to money, normally we go with 2 decimals. How much will the account have at the end of 10 years if it's compounded weekly? So we have the same formula. N was 12 here. Now N is 52. So we replace the N with 52, everybody. Again, add these two numbers, raise it to the power of 520, multiplied by this number, and it gives you $15,288.85, a little bit more. How much will the account have at the end of 10 years if it's compounded continuously? And as you recall, the formula is A of t equals P e to the power of RT. And of course, P is the same P, R is the same R, T is the same T. The base is E. So plug in. And when you use a calculator, you get something even a little bit more, $15,291.20. Okay. So when it gets compounded continuously, it provides more return. Now, with these concepts, both of them, especially this one, there is this concept of doubling. What is the amount of the doubling time for this case, for the continuously compounding case? So I want to go over that, not necessarily this one, but in general. So when it's going to be doubled up, P becomes 2P on the left. So regardless of how much you start, because it drops, you really don't need to know how much you have in the beginning, but we are interested in the amount of time that it doubles up regardless of how much you have. So you have a T, you have 2 equals e to the power of RT, and you are going to take a natural log of both sides. So when we take the natural log of both sides, this becomes ln2. ln of e to the power of RT is RT. And so ln2 is RT. So T is ln2 over R. By the way, one may be looking for R, okay? If in case R is missing, is ln2 over T, okay? But in any event, ln2 over R is 0.04 for this case. So it takes a little bit more than 17 years. I put a bunch of decimals. It depends on how many they ask you, 17.3286. I wanted to get started with a couple of interesting examples like this. And then we're going to go look at some graphs and the concept of exponentials and logarithmic functions. Use the graphs shown to answer the following. And by the way, all of them have the form of an exponential format. F of x is ab to the power of x. Which graph has the largest value for b? Which graph has the smallest value for b? Okay. So generally speaking, as far as the exponential function is concerned, the base must be positive and it can't be 1. Now, which one has the largest base? On the right side, the one that is closest. So let me just show you a couple of graphs. Y equals a to the power of x. A is positive. In this case, a is between 0 and 1. This is an exponential growth, everybody. This is exponential decay. So when y equals a to the power of x, a must be positive, a can't be 1. Domain, all real numbers. Range from 0 to infinity. So what is this x-axis? That is the horizontal asymptote, which has the equation y equals 0. The y-intercept is located at 0, 1. Increasing, decreasing. So for example, 2 to the power of x versus 2 to the power minus x. This is, by the way, the same as 1/2 to the power of x, because 2 to the power of negative 1 to the power of x, that means 1/2. That's the same thing. And as I mentioned, the horizontal asymptote has the equation at y equals 0. Now, the other thing we want to notice, if you have exponential functions where the base is larger than 1, in this case, y equals 2 to the power of x, in this case, y equals 5 to the power of x. As the base gets larger and larger, it gets closer and closer to the y-axis from the right side. On the other hand, for this case, a between 0 and 1, as it gets smaller, for example, instead of 0.5, if you have 0.2, it gets closer. If you have 0.7, it gets further away. Now, when y equals, instead of a to the power of x, is ab to the power of x, then the y-intercept, if you set x equal to 0, this becomes 1. The intercept, instead of 0, 1, is located at 0, a. Which one has the largest value for b? Well, closest to y-axis on the right, just like this one, 2 versus 5, okay, 2 to the power of x versus 5 to the power of x. And in this case, which one is the closest? Look at this one, this one, this one. This is the closest, the D1. Which graph has the smallest value for b? The one that is closest on the left side. And so on the left side, we have this one, okay? And so this one, C, is the closest to the y-axis. Which graph has the largest value for A? Which graph has the smallest value for A? Okay, so we said, if you look at this one, the y-intercept is 0, a, the largest value. Which one of those y-intercepts are the largest value? Obviously, the largest y-intercept is this one. So it belongs to graph of C. The smallest one, this one has the smallest one, right? Graph of this one, graph F, my apologies. So a quick recap. If you have exponential form in the form of y equals a to the power of x, a is larger than 1, it's an increasing function. Between 0 and 1 is decreasing. And domain is all real numbers, range is 0 to infinity. Horizontal asymptote is the x-axis with the equation y equal to 0. As the base gets larger for this case, it gets closer and closer to the y-axis. For the decreasing one, as the base gets smaller, it gets closer. 0.5 to the power of x is the same as 2 to the power of negative x. Use transformation of the graph of f of x equals 2 to the power of x of the function below. State the horizontal asymptote, the domain, and range. So we start with 2 to the power of x. We should know 2 to the power of x looks like that. And it has this one as the y-intercept. So that is 0, 1. So how do we go from here to here? We change the x to minus x. That means flip it over with respect to the y-axis. So reflect with respect to the y-axis. So you reflected, it will look like that. So what happens to 0, 1? Nothing, it remains unchanged. And you get the function that you're looking. Now, as far as the domain range, nothing changes in essence. So horizontal asymptote is still the x-axis y equal to 0. Domain is still the domain for this one also the same, negative to positive infinity, and range 0 to infinity. That hasn't changed. What about 2 to the power of x plus 1? Just go back here and move it up by 1. So you move it up by 1. The result is that now, of course, the asymptote has changed, the horizontal asymptote, and the y-intercept has changed. So this is now 0, 2. This is y equals 1. So what is the result? Well, horizontal asymptote was y equal to 0. That's not the case anymore. Horizontal asymptote has changed to y equals 1. Domain, all of them the same. Range was 0 to infinity, but this one range is now from 1 to infinity. So that's the difference that happens here. Consider f of x equals 4 to the power of x, right? A function that results from the given transformation. We're going to go 3 units up. So add 3 units to that. G of x is 4 to the power of x plus 3. Shifted 5 units left. We're going to go back to original one. That's what they want us to do, work with f of x. And so 5 units left, x plus 5 shifts it to the left by 5 units. Reflected about the x-axis. So you put the negative in front of the y in essence, okay? So minus 4 to the power of x. So h of x is minus 4 to the power of x. Reflected with respect to the y-axis, you put a negative in front of x, so 4 to the power of minus x. I of x is 4 to the power of minus x. So the graph below is the transformation of f of x equals to the power of x, right? The equation of the graph shown. So we had this, now we have something else. We have to figure out what we have by looking at two things. The y-intercept is located at 0, 2. And we have horizontal asymptote with equation y equals 3. So we start with this function. And this has this horizontal asymptote, this y-intercept of 0, 1. It seems to be some sort of a reflection. So if you reflect it and change it to minus 2 to the power of x reflection across the x-axis, it creates this graph. And so this point 0, 1 is now 0, negative 1. And we have the same horizontal asymptote y equals 0. So when we compare these two, it seems to me they're the same. This has just basically moved up. The horizontal asymptote becomes from y equals 0 to y equals 3. It has shifted up by 3 units. So if you shift it up by 3 units, Now this one has coordinates 0, 2. This one has the equation of a line y equals 3. So that is, let's call it h of x equals negative 2 to the power of x plus 3. Logs, if b is larger than 0 and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power 1. We're going to look at logarithmic properties you've had in college algebra. So when you compare the exponential format versus the logarithmic format, they both have the same exponent, they both have the same base. So to understand this, look at the arrow that we draw here. So this means b to the power of y equals x. As long as we can go from logarithmic format to exponential format back and forth, then the properties that follow, you're going to have an easy time. So in the case of a general log, y equals log x base b means b to the power of y equals x. And we get the following. Log 1 base b is 0. Log b base b equals 1. Log b to the power of x of base b is equal to x. B to the power of log x base b equal to x. Okay. Log xy is log x plus log y. All of them have the same base, b. Log of x over y base b is log x base b minus log y base b. Log of x to the power of n base b is n log x base b. What are they? I hope you realize that obviously this goes with the definition that was mentioned here. Also, these two refer to the fact that logarithmic functions and exponential functions are inverse of each other. This is called the product rule, quotient rule, power rule. Now, this is a general case. If we go to a specific case like common log, the base is 10. So when we write y equals log x no base, that means the base is 10. So don't write it like this, right? Write it like this, and know it's 10 to the power of y equals x. So we should be able to make this transition. So for the first one, you drop the base. But let's understand this one, everybody. This means if the base and the argument are the same, the answer is 1. When you don't have the base is 10, so log 10. This one, it says, if you use the base and raise it to the power of x and you take a log, they become the same. So the base is 10 to the power of x. B, the base is 10. 10 to the power of log x equals x. These three, all you have to do, drop the base b. This is natural log. When we write ln instead of log, that means a natural log, which means log x base b, which means e to the power of y equals x. And again, instead of log, we're going to write ln. So this is obvious, but what about this one? Again, when you go back to this one, it says the base and the argument must be the same. When you write ln, the base is e must be ln e, then ln of e to the power of x, e to the power of ln x is x, and these are just the last three properties that were mentioned. And we need to be very comfortable with those. Now, if you look at the graph of y equals ln x versus y equals e to the power of x, because they are inverse of each other, they are symmetric with respect to the line y equals x. What we are looking at is called the change of base formula. What is log x base b? It's log x over log b. Choose any base, for example, a. But if we normally choose base 10, log x over log b, or natural log with base e, ln x over ln b, because of the calculators being able to handle the answer. And now, what this one is, if you cross product here, product of these two is this one. So log base a of b times log base b of x is log x base a. So if you write it in this way, so you keep the first base, and then the argument is the same as this one, and you continue, then the very last one, you pick the argument and you put it here. That's how it works. And of course, you should recognize, if you look at the log function, this has coordinates 1, 0. So ln x is 0 when x is 1. And it's negative when it's between 0 and 1. So over here, it's negative. Over here, it's larger than 1. So that has to do with understanding the graph. Okay. All right. Let's work here. We're going to rewrite each, and we have all those definitions. Go with the arrow. 5 to the power of q is m. E to the power of z is v, and 10 to the power of t is w. 5 to the power of q is m. E to the power of z is v, and 10 to the power of t is w. Rewrite each equation in logarithmic form. 3 to the power of x is y. That means log of y with base 3 must be x. E to the power of k is h. That means ln h must be k. We don't have to write the base, because ln means the base is e. 100 to the power of a is b. That means log b base 100 must be a. So those are the relationship between logarithmic and exponential forms. State the domain, vertical asymptote, and the end behavior of the function where f of x is log x by log of x minus 7. First, let's have a general discussion, and that is, if you graph a log, everybody, log x base 2, log x base e, that means ln x. We don't write it like that. It's on purpose to make a point. I'm going to go over the point that it's supposed to make. Log x base 10. In all of these cases, by the way, the base is larger than 1. Notice, as the base gets larger and larger, it gets closer and closer to the x-axis. In other words, in essence, it grows slower in essence. So if you recall for the exponential, we had the y-intercept of 0, 1. Now we have the x-intercept of 1, 0. We had the domain all real numbers. Now we have the range all real numbers. We had the range from 0 to infinity. Now the domain is 0 to infinity. We had the horizontal asymptote, y equals 0. Now we have vertical asymptote, x equals 0. So this is 1, 0. And these are the information. So in the case of y equals log x base a, where a is larger than 0 and a can't be 1, domain is 0 to infinity, anything to the right. Range is from negative to positive infinity, anything goes. Vertical asymptote in this case is the y-axis, x equals 0. And of course, in this case, as I mentioned, the base a is larger than 1 because it's increasing. Now, if the base is decreasing, looks like that. So if you look at this case, a is between 0 and 1. It's decreasing. For example, y equals log of x base 1/3 or log to the base of 1/3 of x, okay? So that's a general idea. And of course, just for the sake of argument, what's happening here, the base is 10. So generally speaking, looks like that, okay? In fact, again, and remember this one, we don't write the base, this one, we don't write the base. So we start with log, because we want to do the transformation, we're going to start with y equals log x, looking like that. So what do we have here? The same as here, 1, 0, okay. Now, x minus 7 moves it to the right by 7 units. So y equals log x shifted right by 7 units becomes this one. So move this to the right by 7. So this one had coordinates 1, 0. Now this one, 1 and so 1, 0, 1 and 7. Now it's 8, 0. This had the vertical asymptote, which was the y-axis, now has this vertical asymptote. Set this one equal to 0. X minus 7 equal to 0 gives you the vertical asymptote, x equals 7. So again, to find the vertical asymptote for a logarithmic function, you set the argument equal to 0. In fact, if you want the domain, anything larger than, so you set this equal to 0, x becomes 7, anything larger than 7 in this case, because it opens this way. So 7 to infinity, the range doesn't matter, it's still the same, all real numbers. So domain from 7 to infinity, range is the same as before, hasn't changed. So the range is all real numbers. As far as the end behavior is concerned, uh, as x goes to 7, f of x goes to negative infinity. I'm going to fix that in a moment. As x goes to infinity, f of x goes to infinity. So as we go this way, y gets larger also. But this one really, if when we go to calculus, we're going to write as x approaches 7 from the right. Look at number, let's go back to this one, okay? From the left side, it's not defined. It's from the right side of the y-axis that it goes down to negative infinity. So as it moves to the right by 7 units, is on the right side of the 7. This notation means a little bit more than 7, okay? If we have negative, that means to the right, left of 7. So 7 from the right means like 7.000001. 7 from the left means like 6.9999 and so on. So, because I want to make sure that we understand what's going on. We want to look at the following function g of x is ln of 2 minus x and come up with the domain asymptote behavior of the function. And obviously, we are going to start with y equals ln x, which we know it looks like that with the 1, 0 being the x-intercept. So we are going to look at ln of minus x because we see minus x here. And that means if you're changing the x to minus x, that means reflection with respect to the y-axis or across the y-axis looking like that, which means this is 1, 0. Now this one is negative 1, 0. 1, 0, negative 1, 0. Now we want to make it look like that. If we factor the negative out, we get ln of minus parentheses x minus 2. So from here, then this negative 2 means move it to the right by 2 units, x minus 2, shift it to the right by 2 units. So this green one now shifts to the right by 2 units. And so what happens is that this one we said is minus 1, 0. Now the new one is 1, 0 with the vertical asymptote of x equals to. So this point moves to this point. So negative 1, 0 back to 1, 0. And the vertical asymptote x equals to. Now, from the graph, we can see the domain. So the domain is negative infinity to until up to here. So negative infinity to 2. The range is not changing, still are real numbers. And by the way, if you want to go back to this, I want to make a couple of points. You set this equal to 0. I'm sorry, 2 minus x, not that it matters. X equals 2, and that becomes the vertical asymptote. Okay. And 2 minus x larger than 0, that gives you the domain. Okay, everybody, this is how you, in other words, you don't have a graph. You want to get from here to the vertical asymptote, set it equal to 0. You want to get to the domain 2, whatever the argument is larger than 0. It can't be even equal to 0, okay? Now, I want to go over the end behavior. Let me erase my work. So the end behavior, as x goes to negative infinity, as we go this way, this blows up to positive infinity. As we go towards 2, it goes to negative infinity. So we write that, but again, look at number 2. It's from the left side of 2. So instead of 2, really in calculus, we're going to write as x approaches 2 from the left. This means like 1.99999, something like that, okay? 2 from the left. I can't emphasize this enough. What about this function? H of x is minus log parentheses 3x minus 4 plus 3. We want to work on that. So obviously we start with the basic y equals log x, and it looks like this. So this is located at 1, 0. So the very first thing we see is 3x. We're going to change the log x to log 3x. As a result, when x changes to 3x, you shrink it by a factor of 3 along the horizontal axis, okay? So in other words, this 1, 0 shrinks to by a factor of 3. So this goes to 1/3 0. So this is the graph. We originally had it at 1, 0, the x-intercept. Now it's gone to 1/3 0. Okay, so that's log of 3x. Now, when we look at this one here, we are going to factor the 3 out. We get log of 3 times x minus 4/3. And the reason we do that, because this tells us that it has been shifted by 4/3 to the right. So we are going to look at this sort of green one and shift it to the right by this much 4/3. So when we do that, um, this one has coordinates 1/3 0, and it has shifted by 4/3. So we're going to add 4/3 to 1/3, and the new one is located at 5/3, comma 0. The next one, we're going to apply the negative. So because we are applying the negative, we are going to look at the, so I think it's sort of a red one, flip it over with respect to the x-axis, it becomes like that. So reflected across the x-axis, the red one becomes this one. So what happens to 5/3 0? It is still the same location, but it's been flipped over. Then we have +3, which means we're going to move it up by 3 units. So this point goes up by 3 units. So the same x coordinate, this becomes 3. So shift it up. So this now is the graph of the function. Okay, shifts up by 3 units. The result is that this point moves here with coordinates 5/3, and 0 changes to +3. Now that we have the final graph, we want to discuss everything that is given and write everything that we must. So we had this function, we went through it, and we took the 3 out to make it clear what it looks like, and it looks like that. So first and foremost, you have this one located at 5/3 3. Secondly, we have the vertical asymptote with the equation. And by the way, one way just to, if this is given, set this equal to 0. Either this one or this one. Set equal to 0. And that gives you x equals 4/3. So it's very clear. Now, as you can see from the graph, the domain is from 4/3 to infinity, but the range hasn't changed. It's all real numbers. Now, the end behavior, as x goes towards infinity, y seems to be going down to negative infinity. As x goes towards 4/3, it blows up to infinity. And 4/3 really from the right. So as x goes towards 4/3, h of x goes to infinity. This really should be, as x approaches 4/3, from the right. Of course, as x goes to infinity, y goes to negative infinity. That hasn't changed, but this is extremely important to understand.